Hey, back again. So I'm going to address several different problems today, and one of those includes this guy about ozone. So things to know about ozone, it is three oxygen molecules instead of two. And whenever you have two oxygen molecules together, that makes the oxygen gas that we breathe. Three oxygen molecules together is ozone, which I think is like somewhat unstable because we don't have as much ozone as we have oxygen in the atmosphere. So you might have heard of the ozone layer. That's like a protective layer around the Earth that protects us from the sun. I'd also like is slightly reminiscent of chlorine. Like if some people like smell ozone, that's kind of a chlorine smell, even in low quantities. So this particular problem is a little bit backwards in the fact that it tells us what the observed rate law is, and they want us to figure out what exactly is happening. So in my previous video, I was a little bit confused about rate laws having a fraction, so having like products and denominators in the rate law. Now, what's a little bit confusing to me about this is how do you actually enter in those concentrations? Because at the beginning of it, you're actually you're beginning with ozone, ending with oxygen itself. But the idea is that the rate of these things is not constant. So you can't just say like the rate is a particular number. It changes based upon like the time. So it takes time for ozone to break down the oxygen. Now, a very similar example to this is hydrogen peroxide. So to help understand like what's actually happening, I'm going to write down some of this. So hydrogen peroxide. I just thought about this minute, so give me a little bit to figure this out. So hydrogen peroxide is kind of like water, like H2O, but I think with extra oxygen. And that's used to treat wounds. So if you have like an open cut, you pour hydrogen peroxide in, it helps clean it. But if you were to hold that bottle open, part of it would evaporate and just turn into water basically over a period of time. So the oxygen is escaping. I kind of think that this is probably what this reaction is about. Not important, but just to give it a context. So what is talking about here? It says step two because of the rate where step one would be this. So what they're kind of saying is that in many examples, the first step is the slow step. If the first step is the slow step, your entire rate is based on that. If the second step is a slow step, then you have to do kind of more thinking about what's happening. So here's what it's like. I think I used this example before, but I'll explain it more. So I'm going to say washing the dishes. All right, so when you wash the dishes, so let's say you have like a first slow step. So the first step is a slow washer. So they're washing the dishes, and you have a second person there drying them. This is generally like if somebody has two siblings, um, or a sibling. I know as an only child you're not used to this, but like somebody washes the dishes, somebody else dries. So if you have a slow washer and a uh fast dryer or any sort of dryer, really, the overall rate is determined by the slow washer. That's what slows things down. However, if you have the opposite situation, let's say you have a washer of some speed and a slow dryer, kind of everything's incorporated. So here we want to look at two things. You want to look at um, forwards and backwards for the first step, and the for lack of clarity here, this is step two. I haven't prepared any words, so thinking about at them as I go along. So the first step, here's what happens. You have ozone breaking into two things. So you have ozone breaking into oxygen gas, that's O2, and oxygen. This says it's gas, but that's unstable by itself. Like O's don't really exist by itself. That forms into oxygen again. Um, so step two happens very closely after that. This goes both ways. So ozone, or O3, breaks apart into oxygen gas and O's by itself. Oxygen by itself as one atom, but they also come back together. Okay? Because even unstable things, given the fact that they do exist, like says they come back together at some point. So this one goes both ways. So before we look at the equations down here, I'm going to construct them and see how they relate. So for step one, why are we even considering step one? So here's the reason. So it's saying because if the rate were step one by itself, the whole rate will be determined by just this. Where are they getting that from? So the rate always equals some kind of constant. So for the first step, we would say K1. And then we put in the reactant, which would be, sorry, reactant, yeah, which would be the ozone. That would be it. But this is saying that's not the case. They're saying that the rate is something else. They're saying that this rate here is this funny fraction. So I want to see where that comes from. So what you want to do is, if you ever have like test homework or any of this, if you see that the first step is going back and forth, you want to consider two rates set equal to each other using two separate constants, K1 and K negative 1. In this case, we don't know any of that, so we're working backwards for all of this. So if they give us a rate, you want to consider both ways, like what would happen if you did this and what would happen if you did that. So if we consider the first step to be slow, the rate would be that. But it's not that. They're telling us not that, so it's got to be something else. That means that the first step is maybe equilibrium sort of thing, and the second step is slow. So these two steps match the previous video that I made about equilibrium being first and slow being second. So we're gonna go from that basis. So step one is ozone breaking down into oxygen and oxygen gas and oxygen by itself. So the rate would be this. So rate equals some K. I'm going to call it K1 because of the step being the first step. And it would be based on the reactants, which will be O3. And the second step, the first step going in reverse would also be the same rate. So I'm leaving it as R, K negative 1. So what I'm expressing here is what would happen if you take step one and went the opposite way, this way, going to the left. So in that case, reactants and products are reversed. So the reactants would actually be oxygen gas, O2. And I chose a stupid big font, so I'm running out of room here. So write this down a little bit here. So you give me here the rate. AK, which was going to do the opposite direction, so negative 1. We have the gas, O2. And we have oxygen by itself, O. These two rates are equal to each other. So looking closely in lieu of writing another thing, that's what they're doing here. So you notice this step, the arrow pointing to it is we have this one, R equals K1 and ozone, that's this. And then we have R, the same rate, O2 and O. it's the same rate because you have it going back and forth, being created and being broken apart and coming back together at the same time. Now, after that, we're going to solve for O. Now, the reason why we're doing that is because the rate law is supposed to be formed on the slow step, not the first step, it's the slow step. And it's supposed to involve only reactants. So our starting point is actually step 2 here. Now the rate of step 2, let me get that K2 in there. So we got the step 2 rate law is a K2, so it's different than the other Ks. And we have the reactants, the things on the left side. That's this. So we got oxygen just as a element by itself, and then ozone. And when those two things collide, the reason why I'm saying things is because oxygen is the element by itself, and ozone will be molecule. Combine, we have, well, that'll be 4 oxygen atoms, which will form 2 oxygen gas molecules. That forms the right side. That's this. That's how that works at a molecular level, and it's good to understand those because you understand the equations better if you understand like what's actually happening at a molecular level. So get all that, and we're going to solve for this guy because our original rate law involves something we don't want. We don't want O. Now think for a second why you don't want O. Why is that not okay? What is O? So look at the equations and what you would call that. O appears here and here. It appears as a product in the first one and a reactant in the second one. And in the end, it doesn't appear at all. So if it's not at the beginning and it's not at the end, it is intermediate. So you have O is an intermediate, and intermediate should not appear in your rate law. Okay, I wrote this for the first one, but I just want to reiterate that step that's important because that lets you know like what could be right or wrong. So intermediates do not appear in rate laws. So if you write a rate law that has an intermediate, that's okay, but that means you have to use some mathematical substitution, like you do with like lines meeting, to solve it. Let's see what happens there. So we solve for this O. So we get O equals all these guys. So what we're going to do is write the first rate law based on the slow step. That's not it. Ignore that what I just said there. Step 2 is the second rate law. Okay. So we're going to use this step to write our final answer. And so this step is based on the slow step, which we base our final rate law on, but the variables are wrong. So the step 2 rate law is not wrong, the variables are wrong. We have to fix that. So we say rate law equals K2 and this and this. Okay, so what's wrong with that? We'll fix it. So we have rate law is K2. That's fine as it is, K2. Just a number. Oh, we already solved for O. Oh, we got what's in this right here. So we have K1 and the ozone. 3 divided by, we have K -1 down at the bottom. That's the reverse reaction of the first step, and O2. Now, the last thing we have to do is simplify all this. So we have all these Ks. Those are all constants. Those are just numbers. So you bump that down to just being okay. So now we're getting close to our final answer. We have the rate equals some kind of K. And then I'm going to take all this and copy that. So I'm going to say O3 over O2. That's a 3 right there. Okay. I feel like I'm missing something because it doesn't match the first thing. Okay, so what I'm missing is this extra O3 right here. So let me put that in. Okay, so O3. And so we have two ozones there, O3 and O3. And that's how you get the squared right here. So all this was solving backwards. Again, bumping down things into step 1 and step 2. So I'm going to reiterate things right now. So no new information, just more explanation. Step 1 was a equilibrium step. So when you have equilibrium, that means that something's being broken down into two things, but also being reconstructed into one thing. So you have ozone being broken down into oxygen gas and oxygen as an atom by itself. But then you also have oxygen as a gas, the two atoms together, forming an oxygen molecule. Plus an extra oxygen atom being together to form ozone. That is happening at the same rate back and forth. So that's the step they call equilibrium. And the slow step is that little extra oxygen by itself plus ozone forming oxygen gas. That's the slow step. Your initial thing you write is based on the slow step, but your slow step might have something that is not allowed in the rate law. What is never allowed in the rate law is your intermediate. So here, what happened? We had, finding another color, our step 2 rate law was all this. All right, so that was based on a K, which call it K2 because it's the second step. And our reactants, O by itself and O3. Good rate law, but O is not allowed. The reason why O is not allowed is it's because it is a intermediate. It does not appear in the beginning or the end. Can't have it. So the reason why we can't, the way we fix that is that we do some algebra with the first step. The first step, you make two equations. You make the rate going forward and the rate going backward. The rate going forward is this. It says R and K1O3. That is based on the reactant going forward. The second one, we use the same R. We use the same R because forward and backward are the same. Produces and goes back same rate. We say K and a -1 because those are related. And then we say these right here. On the right side, that's normally the reactants, but if we reverse it, those are the products. Like I said that the opposite way. Anyway, you get the idea that if you switch it left, it becomes right becomes left, vice versa. You set those equal to each other and you solve for the thing that you want to get rid of. What do we want to get rid of? The intermediate O. Once we do that, we solve and we get some kind of rate law. And then the rate law is this right here, which we're given in the first place because this is a giant backwards problem. And it's asking you to find out why it is the way it looks the way it is. So I guess that's it. Again, a lot of words, but I guess whatever works. Bye.